Hi everyone, welcome to session 9 of our course, Happy Learning. Last class we had seen a formulation problem relating to a brick manufacturing industry where three types of bricks had to be manufactured with the restrictions in the problem relating to budget availability, kill time, operating time availability of skilled and ordinary labor. And there was also a condition in the problem uh, telling about the wastage of each type of brick being produced and which had to be incorporated in the objective function, which was to maximize the profit. So I think you would have all understood that problem. So we will go for some more examples in today's session. Now we'll see the exercise number 5, which is yet another interesting exercise. A contractor is planning a job that will require large quantity of gravel and sand. There are two pits A and B from which he can obtain these materials. Analysis shows that materials from pits has the following composition, that is, which is shown in the table below. It costs him rupees 120 per cubic meter of material handling from pit A and that of rupees 230 per cubic meter from pit B. Formulate as linear programming problem. So let me explain this problem. So we can see that there are two pits which may be owned by the contractor, and from each of the pits he has to dig the soil, and while digging 1 meter cube of soil from pit A, it will cost him rupees 120 rupees, and from pit B, if he digs 1 cubic meter of soil, it will cost him rupees 230. Now 1 cubic meter or 1 unit of soil taken from pit A will give him 20% of gravel. That 1 cubic meter of soil excavated will have 20% of coarse gravel, 15% of fine gravel, 25% of fine sand, and 40% of coarse sand. The total making up to 100%. Similarly, 1 cubic meter of soil excavated from pit B will have 30% of coarse gravel, 40% of fine gravel, 20% of fine sand, and 10% of coarse sand. Now the right extreme of the table gives what is his minimum requirement per day. He is requiring coarse gravel to be at least 2000 cubic meter, fine gravel has to be 2500 per cubic meter. That means whatever is the soil he is excavating from these two pits, it should give him a minimum requirement of at least 2500 cubic meter of fine gravel. Similarly, the soil excavated from pits A and B should give him at least 5000 cubic meter of fine sand. The requirement with respect to coarse sand is 0 for the contractor, meaning if he will definitely get coarse sand also, but then he is not going to use it for his purpose. He will discard it. So this is how the problem has been formulated. Hope you are able to understand the problem, students. Now tell me, what are going to be the decision variables in the problem? Please think over and tell. Now we have two decision variables. Hope you have got it right. Decision variable x1 would be the number of cubic meters of soil to be excavated from pit A, and x2 will be number of cubic meters of soil to be excavated from pit B. So these two are to be known to him. Okay, these two are the decision variables in the problem. And what is the objective function? What type it is? Objective function is of the type cost. You can see that cost of material handling is given to us. So it is minimization type. So we need to minimize the total cost of extracting the soil from pit A and pit B, which has to be minimum. So the total cost has to be minimum. So we have 4 constraints, each of the constraints with respect to each of these ingredient requirement for him. So let us go to the solution of the problem. Now for understanding sake, I have taken the same table here. So from this easily we can retrieve the data. So we can see that first we have to always represent our decision variables. So I have written x1, two decision variables are there, which is x1 and x2. x1 is relating to number of meter cubes of soil to be excavated from pit A, and number of meter cubes of soil to be excavated from pit B is x2. So that is our requirement or the decision variables. And the objective function for the problem is maximization type. So minimization type, where we need to minimize the total cost of extracting x1 units from pit A and extracting x2 units from pit B. It has to be a minimum. So the minimization of Z is indicating total cost here, which is equal to 120 x1 plus 230 x2. That is, if I extract 1 cubic meter of soil from pit A, it will cost me 120 rupees. I am going to extract x1 units from pit A, so my total cost is going to be 120 x1. Similarly, I am going to extract 1 unit extracted from pit B will be costing me 230 rupees. I am going to extract x2 units. Therefore, my total cost of soil extracted from pit B will be 230 into x1. So that is our objective function. Now 4 constraints are there in the problem. First constraint is with respect to coarse gravel. So coarse gravel availability is going to be 20% of whatever is being extracted. So from pit A, the coarse gravel, I'm going to the total quantity extracted is x1 units, and of which 20% is going to form coarse gravel. That means it is going to be 20 by 100 into x1 plus the requirement of coarse gravel, or the what he gets from the pit B will be 30% of x2. So 20 by 100 into x1 plus 30 by 100 into x2 should be satisfying the minimum requirement of 2000 cubic meter. Therefore, whatever is extracting should be satisfying the requirement, meaning that it cannot be less than equal to, it may not be equal to exactly also. So the appropriate inequality here will be greater than equal to only. So 20 by 100 x1 plus 30 by 100 x2 greater than equal to 2000 cubic meter. Similarly, with respect to fine gravel, we can write it as 15%. So 15 by 100 into x1 plus 40 by 100 into x2 greater than equal to 2500 cubic meter. The third is with respect to fine sand, 25 by 100 into x1 plus 20 by 100 into x2 greater than equal to 5000 cubic meter. The last constraint is with respect to coarse sand, which he is not requiring at all, but however, he will automatically get it when he is extracting the soil. However, he is going to discard it if it comes. So it is going to be 40 by 100 into x1 plus 10 by 100 into x2 greater than equal to 0. So that is what is given here. You can write this as greater than equal to nil or 0. And finally, the non-negativity constraint, which is x1 comma x2 greater than equal to 0. So hope you understood this problem, students. Any doubts, please post it onto the discussion forum. Now we'll move on to another interesting example, which is a problem with mixed set of constraints. So far, the 5 problems that we have seen in formulation, we have been seeing the problems as with respect to only less than equal to or only greater than equal to. And so far, we have not seen any equal to type of constraints in the examples we have seen earlier. But in this problem, we will have problems with constraints with all the 3 types of inequalities. So let's go to the problem. A construction company has alternatives for construction of 2-bedroom houses, 3-bedroom houses and 4-bedroom houses. So 3 alternatives are there with the construction company. The company wants to establish the number of each type, if any. It may be there or may not be there. So the number of each type of 2-bedroom, 3-bedroom and 4-bedroom houses, if any, that will maximize the total profit subject to the following restrictions. So maximization of total profit is our objective function. So we need to maximize the total profit of selling the 2-bedroom houses, 3-bedroom houses and 4-bedroom houses manufactured by the company or being constructed by the company. Now the constraints that are given here are the total budget is limited to rupees 40 into 10 power 7. So budget restriction is given. The second constraint is the total number of units must be at least 300 for the venture to be economically feasible. Meaning the total number of units are the total number of 2-bedroom plus 3-bedroom and 4-bedroom houses that is going to be constructed by the company should be at least 300 for the venture to be economically feasible. Third constraint is with respect to the maximum percentage of demand of each type of building based on market analysis, which is given as follows. That is, after conducting a survey in the market, they can identify what is the percentage of 2-bedroom house on demand in the market. Similarly, number of 3-bedroom house on demand and number of 4-bedroom house on demand. So here he says the number of 2-bedroom house should be 60% of total. So the total is total number of 2-bedroom plus 3-bedroom plus 4-bedroom. Of that total, 2-bedroom house will form 60% of the total. 3-bedroom will be forming 25% of the total. 4-bedroom houses will form 15% of total. And they have also given us the building costs and profits in the table. The unit cost of each type of building, each type of bedroom houses, and the net profit of each unit of bedroom houses are given to us. So let us go to the problem. So it's really very interesting. So both cost and profits are given. So you should understand that cost is given, unit cost is given here to relate to the total budget restriction. So for the budget restriction, the cost is given and net profit will have to be incorporated in the objective function. Now please identify what is going to be our decision variables. So yes, you're right. The decision variables are number of 2-bedroom houses to be manufactured or to be constructed by the company, number of 3-bedroom houses to be constructed by the company, and number of 4-bedroom houses to be constructed by the company. So X1 will be number of 2-bedroom houses to be constructed, X2 will be number of 3-bedroom houses to be constructed, X3 will be number of 4-bedroom houses to be constructed. So 3 decision variables are there in this problem.